Great pleasure to be there. The last morning session of this wonderful meeting with Dexter. So we'll give a wonderful.
Okay, thanks, Kleene. And thanks to everybody for coming today. It's wonderful to see you. I can kind of barely see you out there. I'm a little blurry. Forgive me. Of course, it's a great pleasure to be here. Prakash and I go way, way back. We're kind of like the Han Solo and Lando Calrissian of computer science, I think. Or maybe the Han Solo and John the Hutt or something like that. But I just want to tell one story about Prakash. So, of course, Prakash and I have been working together for a long time. We taught a course together at Cornell about, must be close to 30 years ago on duality and computer science. This is way before anybody else was thinking about it. And I was just heartbroken and devastated when Prakash left Cornell and went up to McGill. We worked together over the years. I went up to visit him last year, and he said, well, why don't you bring your tennis racket and we'll hit a few balls around. And I said, no, I haven't actually picked up a tennis racket in 10 years, and I don't know if I can even play. I had shoulder surgery, and I don't even know if I can do a backhand. He said, no, don't worry about it. Just bring your racket up, we'll hit a few balls around.
That's cool.
So,
that's what it takes to beat Dexter.
yeah, so, yeah. So I said, no, I'm really rusty too, just, don't worry about it. So I get up there, and the guy has signed me up for a tennis tournament. So this is, so my humiliation was complete after that day. And no, this is the kind of standard that holds us all to, and both in science and in life. So for that, I'm grateful. Okay, you might notice that the talk title is a little different from the one that's in the proceedings and the paper that's in the proceedings. I had a sinking feeling after I sent the paper in. I went to look in my notes for the talk, and I saw this file with the title Oxford last year, and then I had the sinking feeling that, well, I've already given that talk here last year. So I decided to talk about something different so as not to bore people. This is something that I'm working on currently with my great students, Ben, Costas, and Ulrich. And so I'll sort of bring you up to speed of what we're working on. Okay, so this is something that has to do with, there's a little bit of duality in this. So that's suitable for the occasion. It's about Kleene algebra, reasoning in Kleene algebra with tests, so reasoning equationally. We often, when we do this practically, we often reason in the presence of some assumptions. So typically we're working with Horn formulas like this, where this S equal T is typically some task that was put in before us. So maybe we want to prove the equivalence of an optimized, unoptimized program, source and object of a compiler. Lots of examples of this. Whereas these premises that come up, these are the verification conditions that must be true. And it's convenient to actually separate the theory of the underlying domain of computation from the more propositional action of program manipulation, which is what Kleene algebra is all about. So you reason equationally at the propositional level in the presence of these assumptions after you've abstracted away. You've verified the assumptions once and for all in the theory of the domain of computation. And that's a good thing to do because often the domain is undecidable and you really don't need the whole theory of it, you just need small pieces. So the types of assumptions we usually work with are commutativity assumptions, which say things like setting x equal to 4 can commute with setting y equal to 3. They don't affect each other. If you do some action, it causes something to be true, or you don't need to do an action because something is true that makes it redundant. So these are the kind of premises that you see over here on the left, and then you reason in the presence of those things. What we really mostly deal with are Kleene, not the full free Kleene algebra, but Kleene algebra modulo these equations on the underlying domain. And what comes out is this notion of language model. It turns out that anytime we can get a completeness result, anytime we can get a fast decision procedure, there seems to be a language model around that makes that possible. So it's worthwhile looking at this this general class of language models and seeing what's going on there to see if there's something general we can say about why we can get fast algorithms, why we can get completeness results in those cases. Most of the examples that I know about, static analysis, I'm going to tell you about some of these. Netcat is a very interesting recent development in this area. Mutable tests, these are all examples of this. Typically, we want to take a class of Kleene algebras and consider the class modifiers. So consider the class, the sub-variety, or sub-quasi-variety defined by a set of monoid equations that are particular to the application. And often this gives you free models. It's desirable when it does so, because this is what completeness means when you get a free model. So it's like the Kleene algebra modulo of the equations, Kleene algebra theory modulo of the equations gives you an equational theory, and then you have the equational theory of the language model, and those things should coincide. And that's always a good thing when that happens. But what I'd like to talk about today is I'd like to figure out why in the same cases you often get a fast decision procedure by simulation-based decision procedure, so when that happens. It doesn't always happen. Okay, so just to remind you where we are, where we're starting from. So let's start with this is the axiomatization of Kleene algebra that I like to work with. It's just an idempotent semi-ring with these axioms here under plus and times, 0 and 1. Where the order is defined this way, you get a partial order, and then a few axioms for star that essentially say that, well, these two together say that P star Q is the least solution of this linear affine inequality. And then by using matrices of the Kleene algebra, you can extend that to n linear affine inequalities and n unknowns. The primordial language model is, of course, the regular sets of strings. And you form these models. Usually they are models consisting of sets of elements of some monoid or some partial monoid, some typed monoid. So for the regular sets of strings, this is the simplest one. The underlying monoid is just the free monoid on generator sigma. And the Kleene algebra operations are defined this way. Plus is just union, times is this. Is just this set composition or concatenation, and then star is just the union of powers of A. And this is the free Kleene algebra on generator sigma, so its equational theory is the same as the equational theory of the whole class. Now, for decision procedures, for the case of regular sets, or for the case of regular expressions, equivalence is decidable in p-space. It's p-space complete. That goes back to Meyer and Stockmeyer. If you go back to their paper, you'll see that it's actually quite an inefficient decision procedure that they give. It's quadratic space and exponential time in the best case. It's almost always exponential space. You non-deterministically guess a string in the symmetric difference of two automata. You convert the two expressions to automata and then try to guess a string in their symmetric difference and simulate the two automata. So this is a non-deterministic algorithm. You convert it to deterministic using Savage's theorem, and that's quite inefficient. There are much more efficient decision procedures that have been studied over the years. I think the world record right now is due to Bonke and Poos a couple of years ago. It's bi-simulation based, uses a very efficient representation of regular expressions using Antimirov derivatives, use of the Hopcroft-Karp union fine data structure, which is very efficient, and up to techniques to improve performance. They have a full implementation in Coq, and it's actually, even though it's a p-space complete problem, in practical cases it tends to work, and it tends to halt and give you an answer. So even though in the worst case it could run for exponential time, it rarely does in practical instances. So just to expand on this a little bit, this technique is based on the notion of Brzezowski derivative, which goes back to Brzezowski in way back, and was espoused by Jan Rutten and Alexandre Silva's thesis. You can think of a finite automaton as a coalgebra for this very simple functor consisting of a pair of maps, which I like to call the observations and the continuations, or the actions. And the final coalgebra for this functor is this semantic Brzezowski derivative, which operates on sets. The structure map of the coalgebra consists of observations that just test whether epsilon is in a set, and then continuations indexed by the letters of the alphabet that just take that letter off the front of strings in the set. And that derivative is that structure gives you a coalgebra for this functor, and it is the final coalgebra. Now you can also define this operation syntactically on regular expressions. Here's an inductive definition of another coalgebra for the same functor. For expressions, you just have a homomorphism, a Kleene algebra homomorphism into the two-element Kleene algebra. And then for the continuations, they're defined this way, and this is, it turns out that the map that takes you from an expression to the set represented by that expression is the unique coalgebra morphism to the final coalgebra. And it turns out that up to associativity, commutativity, and idempotence, you only get finitely many derivatives if you iterate this operation D, and that's what gives you a finite automata. Okay, you can, this also happens with Kleene algebra with tests. So here's another example where we get a language model. So what I want to do is add Booleans to the Kleene algebra. So I'm going to designate a subset of K as some Boolean operations, and I'm just going to, by fiat, axiomatize it by saying the whole space is a Kleene algebra, the subspace with this extra operation of negation on these elements is a Boolean algebra, and that B is a subalgebra of K with respect to the idempotent semi-ring operations. And once you do that, you can encode standard imperative constructs like if, then, else, and while, do this way. It subsumes Hoare logic. You can do partial correctness assertions, and Hoare-style rules become universal Horn formulas of Kleene algebra. Now there is, in this case, also a language model. Okay, this is what the language model looks like for Kleene algebra with tests. It's based on the notion of guarded strings, which were first studied by Kaplan in '69, quite a ways back. So let's take some action symbols and some primitive test symbols and form the free Boolean algebra on T. So I'm just going to take all, you can think of them as all truth assignments to elements of T. And so, for example, if T had 3 elements, your Boolean algebra would look like that. It would contain 8 atoms. And the atoms are the minimal non-zero elements. And then you put those together with the action symbols to get these strings of alternating atoms and action symbols, beginning and ending with an atom. And that's called a guarded string. They are the joined irreducible elements of the free Kleene algebra on generators, free Kleene algebra with tests on generators sigma and T. Okay, so this is the free language model for this particular case. We have guarded strings and sets of guarded strings, and then we're going to form a Kleene algebra out of it. It looks very much like the definition that we had before, except with a couple notable differences. First of all, this multiplication operation, the way we multiply sets, we have an underlying multiplication on the strings, on the guarded strings. That's called coalesced product, or sometimes fusion product, or sometimes smash product. It takes 2 guarded strings, and the only time you get to concatenate them is if the final atom of the first one matches the initial atom of the second one, and then you concatenate them together and you eliminate the redundant copy. Okay. So this is very much like a typed multiplication. Okay. And the one object is the set of atoms, which acts as an identity for this operation. The actions have to be interpreted as sets of guarded strings, and this is how you interpret that. It's just the set of all guarded strings obtained by taking any atom in front or in back, and then test is interpreted as the set of atoms that have that test occurring positively. And this forms the free cat on generator sigma n. Okay, so you can also look at this coalgebraically. So here we have a little bit more complicated functor, and our observations and continuations take this little bit more complicated form. Again, the final coalgebra consists of elements of this subsets of guarded strings, and the observations, they're indexed by atoms in this case, and it just checks for a given set whether that atom is in the set. So that's like the final observation. And then the continuations take an atom and an action and try to take that off the front of elements of A, and the derivative gives you the set of strings that you have left. Okay. So far, so good. And again, you can define this in a very nice way, inductively on the structure of regular expressions. So you can get a syntactic version of this derivative. And again, the same relationship holds between this derivative. So you get finite kind of an automata theoretic view of this, and then the set of guarded strings represented by E is the unique coalgebra morphism to the final coalgebra. All right, so this is the rule. And there are other examples too. Let me give you a rather practical example. Okay, there's development recently in the area of software-defined networks where CAT has been adapted to give a language for network manipulation. So the idea is you want to specify some operations in your network, and you want to be able to talk about forwarding of packets and dropping of packets and filtering, and you can do a lot with this language called, well, there's a precursor to this called, I don't remember what the language itself is called, but it's part of this frenetic suite that people have been working on for a while, my colleague Nate Foster in particular, and we got together with him and determined that CAT was just the right thing to contribute to this operation. So there's modification of CAT to do these things. You can do quite a lot with it, and we had a paper last year in, or I guess it was this year, wasn't it? Was it this year? Yeah, it was this year. Okay. So this is some of the extra axioms that we get. So we start with CAT. We have all the operations of CAT, but they're interpreted differently in this language. Not interpreted quite the same way. And then in addition, we have these actions and tests that you can think of this as just setting just a constant assignment that sets the value of some field in a packet to some value. So you can think of this as, you know, your packet comes in and there's a header that has some IP address. So you might be setting the IP address to something and then setting the port that you're going to send it out on to some value. And that's what these guys do. And then you can test whether some IP address falls in some range, something like that. So in the abstract, you have actions and tests, and then some axioms that describe how these things interact with each other. Let me just take a couple of them. So, we can also duplicate a packet, because if we want to, if we want to talk about packet histories, what can happen over time, we allow duplication. Okay, this one says, if you set the value of x to a value n, set a variable x to a value n, and then you test y equals m, those two operations commute with each other if x and y are not the same variable, not the same field. Kind of an obvious thing. This one here, for example, says if you set x to n and then immediately set it to m, then the second one overrides the first. Now, we can abstract away from this a little bit by considering so-called complete assignments and complete tests. And they form atoms of a Boolean algebra. These guys form, I'm just going to consider it as just a single symbol. Okay. We can actually, under these axioms, under the netcat axioms, you can massage everything into the form where it's a string over these P and these atoms. These are atoms of the Boolean algebra. And then this is what the axioms look like after that. So we can reason in this more refined or more ethereal atmosphere. This thing here says that if you execute P, alpha sub P, these things are in one-to-one correspondence, right? The atoms and the actions. And this says if you do the assignments in P, then the tests in alpha sub P will all be true. So tests are redundant. This says if the values are already something, then you don't have to reset them to the same thing. And this says any setting of values overrides a previous setting of values. And dupe does not change the value of the test. Okay. Now the model is quite different. It doesn't look like a language model. It's a packet forwarding model where programs, which are Kleene algebra expressions, are mappings from packet histories or packet traces to sets of packet traces. So the idea is you're sending packets out. Some packets come in and you send them out. So these are like this is like a filter that takes things in and pushes out a set of packets. And you could drop packets, so the output here could be the null set, for example. The difference between this and the normal way of thinking of Kleene algebra plus is that this is conjunctive. So the plus means do all of these things. It's like it's not non-determinism, not non-deterministic choice anymore. And sequential composition is just Kleisli composition of this map. What? 8 minutes? Okay, good. So then, but this satisfies all the cat axioms. So again, we have a language model, and this is what our reduced strings look like. And now we can do the same thing we did before. We have alpha, x, y, q, where alpha, x, so these are strings in, I'm going to call them netcat reduced strings. They all look like this. Anytime I have alpha, x, p in A, and alpha p, that has to match p, y, q, they can concatenate them together and remove the p and the alpha p. Okay, and this is what my identity looks like. And this is the free netcat on its generating set. Now, one can come up with a coalgebraic view of this, and the final coalgebra looks like this. Now, I'm taking advantage of the fact that actions and tests are in one-to-one correspondence, because this is now looking like a matrix over 2. It's an act by act matrix. And the derivative, this is the final coalgebra, just like this, as before. And now, because I'm thinking of this as a matrix, I can actually give a very succinct definition of the derivative. So this is like encapsulating before. Remember, I have these subscripts down below, alpha, beta. Here I would have alpha, beta, but it's just talking about the alpha, beta entry of these matrices, but I can express the derivative itself in terms of matrices. So it's a very nice, concise way of doing this. Final example, mutable tests. So here I want to add a little bit of structure to Kleene algebra to allow me to think of it as setting a Boolean value and testing the value of the Boolean value of a Boolean variable. These are the axioms for mutable tests and some consequences that you can get out of that. You can see that this looks a little bit similar to what we had on the previous slide. Some facts about mutable tests. If you just take a set of n mutable tests, the free algebra modulo the axioms on the previous slide are isomorphic to 2 to the n by 2 to the n matrices. In fact, it's a tensor product of n copies of a 2 by 2 matrix. The theory is p-space complete, and an interesting thing is if you add mutable tests to any Kleene, you can add mutable tests conservatively to any Kleene algebra, and you can add it conservatively, which means you can just add the tests and take a commutative coproduct. This means that the tests commute with the actions of the Kleene algebra, and you can do that in a very clean way. And the resulting Kleene algebra is actually isomorphic to the 2 to the n by 2 to the n matrices over K. Now, a really interesting thing about this is we have a decision procedure in that case too, and if you take the free Kleene algebra on some generators and some set of mutable tests, and you put them together, both cat and b bang are p-space complete, but when you put them together, it becomes exponential space complete. And I don't know why that should be true. Well, I do know why it should be true, but I think I'm going to skip some of this. I want to get to the interesting part. So this is a general construction that I think captures all of all the examples that you've seen before. Really what we have is a small category with a length function that allows us to measure how long strings are. So you think of the elements, think of the morphisms of the category as like strings, and we have, so this is just actually a functor. You can think of it as a functor into n, thinking of n as a category on one object, satisfying this condition. And I'm going to call observations the guys of length 0 and actions the guys of length 1. And all of our examples are instances of this. So I have a small category with length, and let's say that sigma n O generates C. Then here's some facts. Finitely many objects, because you can't have any more objects than identities. Only finitely many morphisms of each length. Each morphism has a unique, not a unique decomposition, but a decomposition into actions. And there's a finite co-multiplication and a finite co-iteration defined this way that are going to allow us to define set theoretic models. Okay. All of the examples that we've looked at are instances of this structure. So this is how we get the coalgebra out of it. If I have a category C with length, then I get a partial algebra of this form, where consisting of two morphisms from, if you take something from O, you just inject it into S. S is the set of morphisms of the category. And if you have an action and an element, a morphism, you can put them together this way, provided it's defined. Okay, the codomain and the domain have to match. And now you can create a coalgebra by just very simply, okay, I'm doing this for an arbitrary k, by the way, but think k equals 2, that's how we get the language models, but you can do this for any k. And all you do is just compose, to get this map, theta hat, you just compose any input a with theta, and that gives you, and then use this isomorphism, and this gives you a mapping from, this gives you a coalgebra that you can use that looks like a Brzezowski derivative. So here's the final form of theta hat, consists of two functions from a set of morphisms. These are my observations, these are my actions, and this is looking like a Brzezowski derivative. And this is how they all come from in a kind of a general view. You can generalize this to an arbitrary Kleene algebra in quite a straightforward way. You can describe matrix multiplication this way. Let's see. From this you can actually, because we have a finite co-multiplication and co-iteration, we can form a Kleene algebra out of it. This is where the set theoretic thing comes from. This is my definition of star. It's a little bit hairy, but it's not really too bad when you think about it. And this is where we get it from. Yep, almost done. And this is a Kleene, the theorem is this is a Kleene algebra with derivative. Special cases, all of my language models, you get formal power series this way. And so a lot of constructions we know about are actually special cases of this. Okay, and I think that's all I wanted to say. Happy birthday, Prakash. Thanks a lot for everything, and I'll take some questions if anybody has any.
Any questions? Yeah, Prakash?
Can I ask my obligatory probability question? So,
Yep, sure. Yes.
If you interpret these tests as taking values in 0, 1, does it also go through interpreting tests probabilistically?
I don't know, but I would suspect that you can do something there. I haven't even got there yet. I haven't told you about my conjecture. So, so I conjecture that this always gives you a free language model. That's what I'm working on right that's the fundamental thing that we need to solve before we go on to. I think actually you can probably generalize this to other non-Kleene algebras, things that are weaker axiomatization. So things like probabilities, or things that don't satisfy idempotence, for example, where you can count stuff. I think there are lots of things you could look at here. There's a million questions you could ask.
Do you have the decision procedure in general?
No. Not yet.
Okay.
Maybe by tonight.
Okay, thank you very much.